Hey everyone, welcome back for another deep dive with us. This time, we're going to be looking at AI and data privacy, specifically VFL, Vertical Federated Learning. And we've got this really interesting research paper to dig into. It's called Just a Simple Transformation is Enough for Data Protection in Vertical Federated Learning. And it's causing quite a stir. So imagine you want to train this super powerful AI, right? But all the data you need is kind of scattered across all these different devices and servers. Well, VFL lets you do that without anyone actually having to give up their private info. Kind of like, I always use this analogy, baking a cake, where everyone throws in an ingredient without having to share their entire recipe. But here's the really interesting thing. This paper suggests that just by tweaking the model's architecture a little bit, we can make it way harder for hackers to actually get at that private data. We're talking about boosting AI privacy without sacrificing performance. It's pretty cool stuff. So to really wrap our heads around how this works, we got to break down VFL and this whole concept of split learning. And for that, we have our expert here to walk us through it. So what is the big idea behind split learning?
Well, you can think about it like a bank and a credit card company. You know the bank has all this customer data. The credit card company has everyone's spending patterns. And they both want to build a model to predict something like credit risk, right? So split learning allows them to team up without directly sharing those sensitive customer lists.
So they're not just like swapping data back and forth.
Exactly. They're essentially cutting the AI model in half. The bank with the raw data handles the first part of the model. And then at this critical point, we call it the cut layer. They transform that data and send it over to the credit card company, who has the labels, things like whether someone defaulted on a loan.
Okay, so this cut layer sounds super important.
It's absolutely critical. It's like the point where the ingredients get mixed together for our cake and where it sits in the model. That really dictates how secure the whole system is.
So the researchers are basically trying to figure out how to protect that cut layer from attack. And you mentioned these feature reconstruction attacks before. What exactly are those?
Well, these attacks are all about trying to reverse engineer the original data from what's shared at that cut layer. It's like someone tasting a piece of cake and then trying to figure out the exact recipe and all the ingredients. The two main ones this research focuses on are model inversion and feature space hijacking.
And those sound pretty intense, model inversion. From what I understand, it's like they're trying to crack a code. The attacker uses the model's outputs to work backwards and reconstruct the original data. Is that even possible?
It is, and it can be pretty effective. But feature space hijacking, that's even sneakier. It's like they're subtly manipulating the model during training to force it to leak private information. It's almost like tampering with the cake batter to change the final flavor, to reveal those secret ingredients.
Yeah, that's not something you want with your data.
Yeah.
So what are the researchers proposing to do about these attacks? They mentioned something about simple transformations. Is that kind of the secret weapon here?
You could say that. They're arguing that applying. Uncomplicated semi-orthogonal transformations to the data and model weights can make feature reconstruction a whole lot harder. Like scrambling the cake ingredients with a code that only you know, the cake still turns out perfect. But someone trying to steal the recipe just from the taste is going to be lost.
Okay, so you're saying these transformations can essentially scramble the data, but without messing up the AI's learning process.
Exactly, and what's even better, they've got the math to back it up. They've provided rigorous proofs to show that this theory isn't just some lucky guess. It's rooted in some serious mathematical principles.
Okay, so you've got this cut layer
Mm-hmm.
and these transformations. But the paper also suggests that a lot of these attacks are successful because models are missing something called dense layers. Now, what are dense layers?
You can think of dense layers as like the ultimate mixing bowl in our cake analogy. They're the part of the model that really scrambles the data, making it practically impossible to separate individual ingredients or data points.
And why are these dense layers so important for privacy?
Well, what the researchers found is that models with more dense layers are actually much more resistant to these privacy attacks. They ran experiments on these popular image data sets like MNIST, Fashion MNIST, and CFR10. And guess what? The models that used a lot of dense layers, they held up really well against both model inversion and feature space hijacking.
So while dense layers sound promising, aren't there other types of layers, like convolutional neural networks or CNNs, that are kind of essential for things like image processing?
That's a great point. While CNNs are fantastic for image-related tasks, they don't scramble data in the same way that dense layers do. It's like comparing a gentle fold to a vigorous whisk. Both have their uses in baking, but that whisk is definitely going to make it harder to separate ingredients afterwards.
Ah, I see. So the key takeaway here is that the type of layers we use in an AI model can actually significantly impact its vulnerability to privacy attacks. That's huge.
Absolutely. And it highlights the need to start thinking about privacy, not just as an afterthought, but as a core part of AI design from the very beginning.
Yeah. This is all incredibly fascinating. But I have to admit, my brain is starting to feel like that well-mixed cake batter we've been talking about. I think we need a moment to digest all of this. Before we jump into the next part of this research, we'll be right back after a quick break.
Sounds good. So before the break, we were talking about how adding these dense layers to AI models can make them more resistant to privacy attacks, kind of like thoroughly mixing those cake ingredients.
Yeah, and it's pretty amazing to think that something as simple as the type of layer used could have such a big impact on privacy. But um, I'm curious, the research also talked about how these attacks often rely on having some prior knowledge about the data. What do they mean by that?
Well, if you're trying to reconstruct a secret recipe just from tasting a cake, it helps to have some idea of what kinds of ingredients are typically used, right? The researchers actually proved mathematically that without any knowledge of the data distribution, these feature reconstruction attacks just won't work, even against a really basic model.
So are you saying that a lot of these attacks are kind of built on shaky ground, that they might not be as effective in the real world as we thought?
Exactly. Their findings suggest that the success of a lot of these existing attacks really hinges on the attacker having this information that might not always be available.
Okay, so that's where these simple transformations come in as a way to further enhance privacy, right?
Right. The transformations can scramble the data without affecting the AI's performance.
But how do they actually help? Is it just about making the data harder to understand?
It's more about masking the true distribution of the data by applying these transformations. You're essentially throwing off the attacker's assumptions about what the data looks like.
So it's like adding an extra layer of encryption to the cake recipe even before it's mixed into the batter.
Exactly. And they proved this mathematically too. They showed that from the server's perspective, remember, the server is the one receiving the transformed data. The training process looks exactly the same whether the transformations are applied or not.
Wow, that's impressive. But it also makes me wonder if these transformations are so effective, why haven't we been using them all along?
Well, for one thing, the awareness of these privacy risks in AI is still relatively new. And as we discussed earlier, there's been a lot of focus on performance and accuracy, sometimes at the expense of security.
Right. Sounds like we're at this really crucial point in AI where privacy is no longer an afterthought, but a core design principle.
I think you're absolutely right. And this research is playing a huge role in that shift. It's not just about proposing a specific solution, it's about challenging our assumptions and encouraging us to think differently about how we build and deploy AI models.
Yeah. And you know what's really interesting is that these findings go way beyond just image data. We've been talking about cakes and recipes, but what about other types of information like text in natural language processing?
That's a great question, and it's definitely something researchers are really digging into right now. While directly applying these image-based transformations to text data might not be the most straightforward approach, the underlying principles are definitely transferable.
So could we use similar techniques to protect sensitive information in language models, for example? Could we make it harder to extract private data from those models without affecting their ability to understand and generate language?
That's definitely a possibility, and a really exciting one at that. Imagine being able to use AI to analyze sensitive documents or personal communications with the confidence that that underlying data is truly protected. That's the kind of future this research is pointing towards.
This all sounds incredibly promising, but are there any limitations to this approach? I mean,
Mhm.
the field of AI is constantly evolving and, new attack strategies are always emerging.
That's a valid point, and it's important to remember that no security measure is foolproof. The researchers themselves have been very upfront about the fact that their findings are primarily focused on specific types of attacks and data. More research is definitely needed to see how these techniques hold up against other threats and in different situations.
So while this research gives us these really valuable insights and tools for enhancing privacy, it's not like a silver bullet. It's just one piece of the puzzle.
Exactly, but it's a significant piece, and it's really starting these important conversations and driving innovation in AI privacy. We can definitely expect to see a ripple effect from this work, inspiring even more research and development of more robust and sophisticated defenses against future attacks.
It's really inspiring to see how much progress is being made in making AI both powerful and privacy
Yeah.
preserving. This deep dive has been amazing, and I'm sure our listeners are finding these findings just as fascinating as we are. But before we wrap things up, there's one more aspect of this research I want to touch on. Remember how we talked about how to measure the success of a privacy defense? Well, the researchers actually challenged the traditional way of doing that, and they proposed a new metric inspired by the world of GANs. Let's dive into that after a quick break. We're back, and before the break, we were talking about, how to actually measure how well a privacy defense works. Because just saying, oh, the hacker couldn't get the exact data, that's not really enough, is it?
No, not at all. A commonly used metric, mean squared error, or MSE. It might tell you how closely a reconstructed image matches the original, but it doesn't tell the whole story.
Right, it's like those baking shows where they try to recreate a cake based on looks and completely miss the mark on taste and texture.
Exactly. A reconstructed image could have a low MSE and still reveal sensitive information.
That makes total sense.
So to get a more complete picture of privacy, the researchers, they turned to this metric borrowed from the world of Jan's generative adversarial networks.
Oh, yeah. Jans, those are cool.
It's called Fréchet Inception Distance, or FID for short.
Okay, FID, break that down for me. How does that help measure privacy?
Well, FID, it's really good at capturing the perceptual similarity between real data and the reconstructed data.
Perceptual similarity.
Yeah, so instead of just comparing pixel by pixel, it looks at higher level features and assesses how similar the overall impression is.
So FID is like the judge in that baking competition who actually takes a bite of the cake and says, this tastes nothing like the original, even if it looks almost identical.
That's a great analogy. And the study used FID to show that their approach, these simple transformations in dense layers, actually makes a real difference in protecting privacy. The reconstructed data might fool a simple metric like MSE, but FID shows that it's not perceptually similar to the original, so sensitive information is still protected.
This whole deep dive has been incredible. We've uncovered some really groundbreaking stuff about vertical federated learning.
Yeah, we have.
We've learned how split learning works, explored these threats of model inversion and feature space hijacking, and seen how something as simple as adding dense layers to a model can make a huge difference in privacy.
And those simple transformations, too, can't forget those.
Right, scrambling that data without messing with the AI's performance, that's huge.
Game changer.
It really is. It shows that we can have both powerful AI and strong privacy. But as we wrap things up, I want to leave our listeners with one final thought. This research focused on image data. But what about all the other types of data out there? Could these same principles be applied to protect text data in those crazy powerful language models we hear so much about?
That's the million-dollar question, isn't it? And one that researchers are really digging into as we speak. Imagine a world where we can use AI to analyze sensitive documents or personal communications and be totally confident that the data is actually protected. The possibilities are mind-blowing.
Yeah, it feels like we're on the cusp of a whole new era in AI, where privacy isn't an afterthought. It's built in from the ground up, and the research we talked about today is paving the way for that future.
I agree.
That's it for this deep dive, everyone. A huge thanks to our expert for guiding us through this fascinating topic. We hope you've enjoyed this journey into the world of AI and data privacy. Until next time, stay curious,